Here's problem 3514. A fish is 80 centimeters below the surface of a pond. What is the apparent depth in centimeters when viewed from a position almost directly above the fish? For water, n is equal to 1.33. Okay, let's imagine a water surface here, and we have a fish below, and the fish is a definite distance, d, below the water. But as we're looking at it, there's going to be a ray coming from this fish that is going to be refracted away from the normal to our eye. So we're looking at this, and we see that apparently the fish is at some lesser distance below the water. It's called d prime. Okay, we know that we have an index of refraction n1 for the water, 1.33, index of refraction n2 for the air, 1.0. And we're going from some incident angle at theta 1 to some refracted angle theta 2. Snell's law applies, so we have n1 sine theta 1 equals n2 sine theta 2. So we would say that index 1 is equal to, index of the water is, let's just assume that we don't know what that is for the moment, would be equal to n2 sine theta 2 over sine theta 1. Index of the air is 1, so this is just theta sine theta 2 over sine theta 1, which we could write as tangent theta 2 over tangent theta 1 if the angles were small. In other words, in the small angle approximation, the sine of theta is equal to the tangent of theta. Now we're going to make that approximation, and I'll explain why we can do that in a moment. But for the moment, we'll just say that n1 is equal to the tangent theta 2 over tangent theta 1. Now if this distance here is x, then the tangent of theta 2 is going to be equal to, if this is theta 2 right here, then theta 2 will also be this angle right here. And hence the tangent of theta 2 is going to be equal to the opposite side over the adjacent side, which would be equal to x over d prime. And then if I look at the other triangle here, we can see that the tangent of theta 1 is going to be equal to x over d. X's cancel out, and we have that this ratio is equal to d over d prime. 1 over d prime over 1 over d is d over d prime. So the index n1 should be equal to d over d prime, or d prime should be equal to d divided by n1. n1 being the index of refraction of the liquid, in this case water. So the apparent depth will be less than the actual depth by a fraction, or by the factor of 1 over the index of refraction for the liquid. Now, why can we use the small angle approximation? We can because we're assuming a little bit of angle here, but if we actually take our observing point above the water, so that the fish is below the water, and then we're actually observing exactly above, then what's really happening is the angles that we've assumed in this original diagram are getting smaller and smaller. Theta 1 is getting smaller and smaller as it approaches 0, and so is theta 2. So we can actually think of this as this exact problem where we're looking at an object at some distance d below, but it actually appears to be some distance d prime below the surface. And hence in that case we have d prime is equal to d divided by the index of refraction. So that being accepted, we have that d prime is going to equal the actual distance, 0.8 meters, divided by the index of refraction, 1.33, and that's going to be 0.6. Should have known that. Or 60 centimeters. So the apparent depth of the fish is going to be 60 centimeters below the water. It's going to look like it's closer to the surface of the water than it actually is.